Guess what? You're one of the lucky ones. You know what I mean by that? Next Wednesday is our magic round. Guess what you're missing? No, you're missing standardized testing. Which,
Oh wait, I have to look it up.
yes you do. Dr. No is going to summon you. When she does, you go make up the test. You don't blow it off, you don't ditch it. I don't know. But whenever she summons you, you go do it. Because if you don't, I get the point. You go do it. So
I'll probably have to get it after
this class
class.
has to do it.
I'm the only one.
Sarah Junior is not involved in the
365.
You're enrolled in AP.
then you don't have to take standardized testing until after 8 weeks. See, this is why you should have taken 8 weeks.
I don't like history though. No, I'm gonna take it right for
Yeah, get that info to me. No, we're just crossing all our T's, dotting our I's. If you don't get it today, just bring it in next Thursday. Not at all. Just get it to me. You're the only junior in this class who's not enrolled in AP. According to the list, not according to the list.
I had so much energy.
Well,
so much energy to go to school too.
Yeah, it's not like
I'm not going to.
which brings us to the first
That was today, right?
Yeah, you can do that.
See me after.
Did I say true yet?
I like
All right, I'm collecting from you your permission slips. Please pass them to the right. If you don't have it today, or if it's not completely filled out, just get it to me next time, but I do need them.
I forgot that I did.
All right, so permission slips, please, to the right side.
I forgot that there were like 3 pages for it. I looked at the finish out the part and I didn't finish it.
It's all right. Huh? It's we're crossing all
Remember
the
you
T's.
were like, as soon as Brian
You
used
get me next time.
I hate like, why is this much confusing? Everyone, 2 and 6.
No, you bring it all here.
Just give it to me as soon as you get it.
Wait, no, not 2 and 6. It was 4 and 6.
All right, everything good?
You get the one about NSC 68?
Yeah.
That was the
Good,
hardest one.
good.
I was like NSA 60.
Maybe you'll get like a Alice the Blow Steve.
I don't even remember the answer to that one. What? Was that
All right. Let's go through all the details of our trip to Magic Mountain, which is when? Wednesday. Okay, first of all, on that day, as a reminder, it's a 246 day. Yes, you are to go to your period 2 class, but you'll be dismissed early. You'll be dismissed at 9:10. We then meet at the flagpole at 9:15 a.m. So attend period 2, but then meet at the flagpole at 9:15 a.m. I'll take attendance, we get on the buses, we then go. The park opens at 10:30. We get there about 15 minutes or so, depending upon traffic, before the park opens. And then while you're at the park, you have to gather data for the assignment. You don't do the whole assignment there. You can finish it up afterwards. I give you a few days to finish it. But you do have to gather data for the assignment. We'll get to that in just a few moments. On the other side of the day, however, we then meet back at the buses at 4 p.m. I then take attendance once again, we get on the buses, and then we come home. We're usually back here at school, depending on traffic, between 5:15 and 5:30 p.m. We have to get back in time for the late buses to depart, so that's why the day is structured as it is. Once again, attend period 2 until 9:10, then meet at the flagpole, and then we go from there. Okay, now the actual assignment itself, let me pass it out to you.
Is there a reason why it's all this now rather than on Monday?
The reason why I'm telling it now is because on Monday during period 2, which is also honors physics, is a short period because of the senior meeting. So that's why I'm doing it for all the honors kids right now. So period 2 got this today, as did period 4. Okay, now, at the end of the packet, there is an additional page here, which I originally had neglected to get photocopied. So this right here is the last page of the packet. So that's the last page of the packet. Okay, now, going through the assignment here itself, it's not a formal laboratory report. It's just a series of problems. It is, however, worth 100 points. It's easy, it's just forces and energy transfer, but it is worth a considerable chunk of points. This is such that you treat it seriously. Okay, now just kind of some of the basics here on the front page of the assignment. Okay, you are to do the following problems. Number 1, Scream or Goliath. Number 2, Riddler's Revenge or Batman or Revolution. And then choose any 4 of the remaining 7 problems. That gives you a total of 6. Some are definitely a little easier than others. If a ride is closed, move on to the next ride. If multiple rides are closed such that you cannot complete 6 problems, oh well, we'll cross that bridge if we come to it. Okay, now notice in bold, there's a big rule here. No typed papers will be accepted under any circumstances. All answers must be handwritten on these handouts, no exceptions. This is to ensure that everybody, of course, is doing their own work. Okay, do each section of each problem in the space that's provided, show all measured values and calculations, make sure you list the proper units and blah, blah, blah. Okay, now, the types of measurements that you have to make while we're at the park fall into these categories. So types of measurements. The first type of measurement that we'll have to make for various problems involves measuring the length of our roller coaster train. So how do you do this? Well, in just a few minutes, I'm going to have you guys get prepared for this assignment by breaking up into groups and doing a couple of things. One of the things that you'll have to do is grab a meter stick from the side rail, and then with your shoe on, measure the length of your foot in terms of meters. The reason why you need that distance is because in order to measure the length of a roller coaster train, you basically have to pace it off. So imagine that the front row of desks here, for example, is the train. What you then have to do is go to the very front of the train, and then going heel to toe, you then count the number of steps necessary to pace off the length of the train. Number of steps multiplied by the length of your foot then gives you the length. Not the length of your stride, like so, but the length of your foot, so you have to go heel to toe. Now, of course, you can shortcut this a little bit. For example, let's say that the train consists of these 3 desks. All you would have to do is say just pace off one of the desks like so, multiply by 3, multiply by the length of your foot, and that then gives you the length of the coaster train. This process literally takes a few seconds to do. But that's one of the types of measurements that you have to make. You have to make this measurement by pacing off. Okay, secondly, speeds. At various portions in some of the problems, you're going to have to make a measurement of the speed of a coaster as, say, it passes the top of a hill. So let's say, as an example, we have right here a coaster hill. Okay, and then what we're asked to find is the speed of the car, or speed of the train rather, as it passes the very top of the hill. But what you have to do is time it. What you want to do is with the smartphone on your smart stopwatch on your smartphone is start the clock when the front of the train is here at the top of the hill, and then stop the clock when the back of the train passes the top of the hill. Because if you know from earlier, the length of the train, L, and the average speed is just distance divided by time. We'll calculate an average here, that'll be good enough for our purposes. Notice that you don't have to be on the ride to make this measurement, of course. You could just be off to the side watching the coaster train crest the hill. A third, masses of fully loaded trains. You basically just have to count two things. You have to count the number of cars and the number of seats. Because then we can come up with a ballpark figure and approximate mass of the train in the following way. As an example, take a look at the first problem, which is Scream or Goliath. Take a look specifically at step 5. So in step 5 it says, assuming that each car's mass is 200 kilograms, that's a reasonable estimate, and each person's mass is 65 kilograms, once again a reasonable estimate, calculate the mass of a fully loaded train. So it's very simply the number of cars times 200 plus the number of seats multiplied by 65. That gives us a ballpark estimate then of the mass of a fully loaded train. It doesn't matter how many people are actually riding the ride when you happen to be there. Let's just assume that the train is fully loaded for simplicity. A fourth. Heights of ride structures. So let's say, for example, we have some coaster with a hill, and it has an unknown height h associated with it. How are we going to get a ballpark estimate of the height? Well, what we can do is, if you can get directly underneath the hill, then what you have to do is horizontally, not uphill or downhill, but horizontally pace off some distance. Let's call that distance here x. So you have to pace off x. And then, if you can somehow find this angle here, theta, then we could just use a little bit of tangent here to figure out what h is. Tangent of theta is equal to h over x. So the height h then is obviously just x tangent theta. But how do you get the angle called the altitude angle here in a problem such as this? Well, one of the other things that you're going to do in just a few minutes when you start to break up into groups is you're going to construct out of a protractor here a little sextant. What we have here is a straw to use as a gun sight, and then we have a plumb bob here that is hanging from the center of the protractor. Because then if you take the protractor and you're some distance away here from the top of the hill, you can then sight through the straw as a gun sight like so to the top of the hill, and then your lab partner will have to measure the angle that is made by the plumb bob's string here with respect to the 90-degree tick mark. That's the same as this angle theta. It basically looks like this from the geometry. So here's our protractor as a sextant, like so. You're pointed like this towards the top of the hill, and then right here is your plumb bob like so, the washer attached to the string. Okay, right here, we'll say is the 90-degree tick mark like so on the protractor. This right here is the angle that we need. This is our angle theta. The reason for that is because if this red dashed line here is off towards the horizon, so that's horizontal, right here is the altitude angle theta on my left-hand diagram. That's obviously the same thing as the angle theta that is made by the plumb bob with respect to the 90-degree tick mark. So that's how you find the angle theta, and then from there it's just a little bit of tangent. However, in most cases, you can't get directly underneath the roller coaster hill. They're, of course, all fenced off. The last thing that Magic Mountain wants is a bunch of little kids running around underneath roller coasters. So then, therefore, if you can't get directly underneath the hill, how would you make the measurement then? Well, it's just then a two-step process. For example, so once again, let's say that right here is our hill with unknown height h. However, let's say that right here is the fence, like so. The fence is some distance d away here horizontally from the hill itself. But you can't measure d because you can't get any closer than this. Well, what you do first is you once again measure here an altitude angle theta, but now we'll have tangent of theta is h over d. There are two unknowns there. We basically need another equation. So what you have to do is then pace off horizontally, not uphill or downhill, pace off horizontally like this, backwards, away from the hill. Pace off once again, we'll call it a distance x. And then using the sextant, you then once again gun sight along and measure now this smaller altitude angle, call this one phi. And now we just got another triangle. Right here is a big right triangle. Once again, we'll just use a little bit of tangent. So now tangent of phi equals h over x plus d. And now you basically just have two equations and two unknowns. The two unknowns are d, which we don't care about, and the height h. What I suggest that you do ahead of time is do the algebra that is necessary, combine those expressions together, and come up with an expression for h that is in terms of the three things that are measured. The two angles, theta and phi, and the pacing off distance x. So you basically have to measure three things here, the two angles and x, then do the algebra, come up with a function here for h in terms of those measurements, and then just use that formula over and over as is necessary throughout the entire packet. Okay, it just takes a few moments to do that. Okay, and then lastly, in terms of the measurements, we can also, it turns out, use the protractor as an accelerometer, specifically on two rides. The first ride is the Grand Carousel, which is the big merry-go-round towards the front of the park. And then the second ride, should you choose to do it, is Swashbuckler. Does anybody know what Swashbuckler is? It's one of the old rides. Anybody know what it is? It's the swing ride. That's where you sit down in the swings, it goes upwards, it then rotates, everybody moves outwards from centrifugal force. On that ride, you could also use the protractor as an accelerometer. Let's take a look at an example. Turn to the Grand Carousel. The Grand Carousel is an easy problem to do. Take a look specifically at step 4 in that problem. Step 4 in that problem is where we use the protractor as an accelerometer. The way that you have to do this is as follows. You would be standing at the very edge of the circle as the carousel is rotating around, and you then take the protractor and hold it out in front of you like this. Let's say the center of the circle is here off to my left. Then from centrifugal force, what the plumb bob will do, of course, is move outwards like this away from the center of the circle. You need this angle right here made with respect to the 90-degree tick mark. The reason for that is as follows. Here's a nice little bit of review for us. So here's our protractor like so. Off in this direction is the center of the circle. And then here's our plumb bob like so. If we take a look at the forces here that are acting upon the plumb bob, we have tension T, the force of gravity mg downwards, and then once again right here is the angle, as I said, that we need to measure. This angle theta on my force diagram is found by taking the tension T and breaking it up into components. Component like so, and like so, where right here is the angle theta. And then if we add things up now using F equals ma, once again a nice little bit of review here. Remember how this works. We have T cosine theta here, canceling out with mg. And then we have right here T sine theta in the direction of our centripetal acceleration, which remember is towards the center of the circle. So we'll have here T sine theta is equal to ma. Like so. If you combine the equations together and solve for the centripetal acceleration ends up being G tangent theta. Excuse me. Like so. So you can measure the acceleration directly, just as g times the tangent of the angle, but of course you have to be on the ride to measure the angle itself. For the remainder of that problem, steps 1 through 3, I have you calculate the centripetal acceleration a different way, and then we just make a comparison at the very end of the problem. It's actually a really easy problem to do. Okay, now take a look at the last 2 pages. The last page of the packet itself, plus the extra page that I gave you. notice that it's a checklist. So this checklist is there to help you just check things off as you go in terms of what measurements you have to make for an individual ride. You don't have to put the individual measurements there on the checklist page. The checklist page is just there for you as a means of you guys just keeping track of what it is that you have to measure for an individual ride. For the most part, you don't even have to be on the ride itself in order to make a measurement, certainly not on any of the roller coasters. The only measurements that you would have to make actually on the ride itself is as I said, on the Grand Carousel or on Swashbuckler with this last type of measurement. So if you don't like to ride roller coasters, in other words, you don't have to ride the roller coaster itself to get the data that you need. All the measurements can be done, of course, when you're off of the ride itself. Now I've structured this activity such that if you're diligent and you kind of know ahead of time what it is that you have to measure, and you perhaps maybe divvy up your work in your lab group, then you can probably get all the measurements that you need done maybe 2.5 hours at the most, if you're careful and you do this quickly. And then of course you can enjoy the rest of the day with your friends for the remainder of the day until we meet back at the buses at 4 o'clock. So once you get the hang of it, you'll find that doing this assignment, getting the data you need, it actually goes pretty fast. Okay, now, over the next 20 minutes or so, we basically need to do 3 things. Number 1, I want you guys to break up into groups of about 5 people, and then have one person come up here and then sign in everybody's name for your group. I'm going to need somebody to claim Griffin, excuse me, and I'm going to need someone to claim Henry in the back of the room. Sorry, I lost my train of thought for a moment. So I'm going to need a couple of students claimed into a group. Have somebody from your group come here and then sign in everybody. And then secondly, you need to measure the length of everybody's foot. Do so, of course, with your shoes on. You're not going to take your shoes off while you're in the park. You need to measure the length of your foot. You'll need a meter stick to do that. Make sure you write down the measurement, however, in meters on the front of the handout. And then lastly, in the back of the room are all the things that you need with the exception of tape. I've got tape here on the desk. But there's everything in the back of the room along the back rail here to construct your protractor like so. Assign a trustworthy member of your group to hold on to the protractor until we need to use it on Wednesday next week. Sean, your questions?
So are these groups, are they going to be allowed to instead of 6 months?
So this is your lab group while we're there. I have to have you guys work within the group here in class. I mean, you could hang out with your friends from other classes, that's fine, but gather your data together as a group just for members here in class. Once you're finished with this, you guys can divvy up the work, by the way, within your group as much as you wish. But once you're done with it, then you can go off and do your own thing for the remainder of the day if time permits. Yes? You can hang out with your friends, but I want you to gather data with the people that are here in your group from this class, okay? Now, it shouldn't take us that long to do all this, maybe 20 minutes or so, and then we'll wrap up and we'll go ahead and move on. So go ahead and do the couple of things that we need here to do. Presumably all of your shoes are about the same size. You're not going to show up to Magic Mountain wearing clown shoes, right? They're about the same size.
Not really.
Wear comfortable walking shoes.
Yeah,
You know, you don't want
alright.
to show up in high heels.
Are we taking Griffin?
Hey, you don't want to show up in high heels.
Yeah, alright. Griffin.
4, okay.
4 is okay, yeah.
You want to be Griffin?
Somebody claim Griffin, somebody claim Henry.
If you want.
I'm not gonna wear these. You guys listen to me? I mean, not that like we don't all want him in our
I'll go right
I'm just gonna take 2 minutes. Anybody else like?
You could trade
If you guys want to trade,
I don't know all the last.
we need a couple.
I don't even know. NER, right?
IE, yeah.
Peace out, Kevin.
Just don't forget, yeah. A lot of people say EI, and I get frozen. I want to get through it.
Excited. You know what? It's all good. I'm gonna get full.
Diego, what's your last name?
Just write
I need to make up my math quiz tomorrow.
Streamer Glide.
Oh, we're doing that now.
Today is Thursday.
Did we do that? Oh, wait, no.
You want to look at my protractor as to how to build it, it's right here. Oh, one thing I forgot to mention about the protractors, this is actually kind of an easy error to make. When you look at a protractor, find on one side where 0 degrees is and where 180 is. The string has to hang from that point, depending upon the middle of that point that is. Depending upon which protractor you get, that may be like 0 and 180 up here, or maybe 0 and 180 over here, and then you would have to hang the string from the middle like that. This is an easy error to make, just be a little bit careful. If you're not sure, bring it up here and I'll show you.
I'll have to take my election being longer than my.
Honestly, do it over the summer as much as I can. I just want my freaking floor. You know what I want floor right now? So bad. No, it's had I'll measure my leg. Nah, you're gonna name it.
Hey guys, Sabrina's gonna be
Okay.
29:30.
No, you're 30. No, I'm gonna take my shoe off and then measure my shoe.
Or you can just go ahead and
That's stupid, right?
That makes me
Be sick. I'm gonna be sick, but. Alright.
I know, but it's my. Oh, yeah.
I'm going to my own version of Go Tell It Late Night. No, it's not my kind of
Yeah, it's all measured up, but you were 30, I'm not wearing any shoes. I was 29.
Just step out and 25.
Oh, men?
Kidding, I used to be like 12 and 13.
No, but
So make sure that you convert your measurement of the length of your foot into meters.
It was 13.
And we have to take the string from the halfway point between 0 and 180. And maybe at the top of the protractor, maybe you'll look at everybody's score is going to do 30
You want to measure?
why is that? If you have so many different
because
shoes.
everybody is an average.
On a foot is what? 30.
Yeah.
30 millimeters of foot. I think it's by the oh wait, no.
Yeah. That's exactly.
I think we should do power teams of 2. Power teams of 2? Yes. Yes. No, they're not being anything done. Nash. Someone needs to
Nash and Griffin, it's gonna be bad.
Yeah, Griffin is gonna go by.
Oh, yeah.
10 minutes.
No, what is it?
We're gonna buy. Oh, mine?
It's going to be you two and then me.
No, actually, I really like to go over right and not listed on this if we have time.
Sure, yeah, of course. I constructed those activities. They're all right.
No, it's great. We're gonna go on 2 rides. All the way up to 3. Stay. We're gonna go on rides towards the next day. We'll go on 2 rides. I go on 1 ride. I want to go next year so bad.
Are there scissors on the desk?
Okay.
There should be a box of scissors back there.
Right here.
So put them on the desk.
And then,
Right.
and then, I don't want to be like us the last one freaking out about getting
Don't worry, we're not.
Make sure that everybody is signed in.
Oh, yeah.
Can I get the straw one. I kind of make it.
Yeah, I don't care. Oh, ew, are you gonna make a noodle? No, don't make a noodle, that's stupid. Go get a noodle. It's a caterpillar.
Why didn't get it wet already?
No, and just said you think squish it up.
Never mind. I'm on your. These are really hard. Just
Wait, can
You're like, yeah,
Why are you being mean to me today specifically?
Because I don't know.
I'm not doing much.
And you know what's I'm making noodle do whatever, caterpillar.
figure out,
Like clover.
So much fun.
Nathan's
That
31.
row.
Yeah, about.
You're trying to hop. It doesn't matter what you.
Guys, I have the attention span of a squirrel.
Why is this?
Okay, great, let's
You put it there or you put it on top of it?
Look,
So I
Let's
did
just
one,
operate.
I'll hit you with the.
yeah, that's not doing anything.
No, because the
Baby,
back.
do I have to hold it to your legs right there?
This tape is so dirty.
Oh.
It is electric.
It's just like
I want the screw
Yeah,
to
You have what?
Like honestly, I think I thought it would be awkward when I Griffin and I
Oh, yeah?
Yeah, that's right.
Oh, okay.
It's all
You have to measure
It's
feet.
all the stars.
Make a protractor, measure like your feet and side.
Whoa. Diego.
Yeah.
Why would you do that? That's crazy.
7 minutes.
Sorry.
Yo, give me a new straw.
Wait, but show it. But to like water. But this is actually.
Ruined it all.
That's what I'm talking about.
I'm all finding you there.
Yeah. Wait.
No, but I was probably on the eyes, I guess like this is the best place I can.
Gotta be.
I thought you were online.
Yeah, I'll need the example back. Then you just show it to a couple. So it's keep it down there.
Oh, you didn't want Discord or one?
Yeah.
The whole like so bad.
I can't wait this joke. Literally get my head under clothes.
Yeah.
Oh, we know.
In my head, I see you having fun.
Do that camera.
Can't
Can't do an accent. No. You know what I'm talking about? No. You can never get a dinosaur.
I've done this trick every year for the last 18 years. I've gone just a couple of times, because I've been on all of them a zillion.
You got X two. My favorite, I have to go to the one.
Goliath is my favorite. I like Superman a lot too. The new one, Full Throttle, is actually good. Yeah, I went on it once last year for the first time. I'm going to-
It's like a pinky.
I just feel like the X two is.
X2 is pretty good. I actually haven't ridden it. I don't like Toxic. The Toxic 2 is actually pretty good.
Oh, I think it's
What's up, Benito?
I just know lots of because I.
Whoever has the rolls of tape, you can bring them up here.
Came out last year. Oh,
Okay, English.
5 minutes.
Irish, why would it be Irish? My last
That was so fun. There's some like dark.
Oh, Godzilla.
Oh, sure.
Bangladesh.
You may be another one.
Is it southern?
What are you missing next week on your trip?
There's
You already
like
say Scotland?
Okay.
Scotland, South America.
Yes, they sure do it. Because if you don't do it.
I said that like 2 minutes
Yeah, this is a common core.
I can help you. Not all South Africans. I know they're all white. You Dutch. Technically, you make Dutch.
Actually, outside Africa.
Dutch. I'm
No, it's not
I got
that great, but I told Dr. No that I was gonna have some
I
juniors.
think Sean, okay, this is really, like, you should have
They still did it. As long as it's
Hey, how's it?
when you work something, eventually.
Is she? I have to pay her.
No, it's the reason why, I mean, I asked you about 8. You wouldn't have to take your shit after.
You know what?
Who's don't
Yeah,
get it?
8 week.
That's right.
But you're not.
Well, there's it's like we have a lot of
No, I did everything.
I'm still scared to take it.
3 minutes!
Yeah, well.
Do good.
No, I know, I can how hard it
We want to decide what.
See that little meeting keep it?
Yeah,
Honestly, I did this so
Not say that, but
it's because of
Remember, somebody trustworthy in the group now has to hold on. Kevin might know you're over there, graduating.
No, you.
Okay, might be a little.
I'll keep it. I think it's
My assessment, my increase. I'm on money. I'm the scaredy cat.
Why are you bullying my teammate?
So much, right?
What?
I never
What?
Don't bully my teammate.
Why does everyone?
Living it up.
Alright, Scream or Goliath?
I'm down.
Like spending $100.
I think I like Goliath. I'm not. That's the one I want to play.
Tells you on.
That way, alright, but I think honestly.
1 minute.
That's my favorite. It's Zealand.
Yeah. Oh no, I've heard it's right. Oh no, I'm gonna go all around. Actually, no. You don't have to go one.
All right, everybody, move back to your regular seats, please. All right, everyone, please move back to your regular seats.
I want to exercise.
Please move back to your regular seats.
I'm too windy.
I will remind you of this next week on Monday, but of course our trip is on Wednesday. Go to your period 2 class until about 9:10 or so. Meet at the flag pole 9:15 and then go from there. Hey, do me a favor, please put away all of these lab materials. Take out your notes. Let's go ahead now and continue here in chapter 16 with sound, specifically the
Sorry, is this the really long unit? You know, you were talking about like there's like a short unit and there's like a really long unit and then.
No, our next exam, don't worry, it's not for like another week and a half or so, something like that. It's not until after the week of Magic Mountains.
And then
there's
there's
the week after.
yeah.
That's our last unit exam, and then the next exam after that is the final.
I got it, and then the next one. Okay.
All right. Continuing with sound, specifically let's describe loudness. Okay, now the word loudness is a physiological term. It's describing our senses. However, what we perceive as loudness corresponds to a new physical quantity for us, what is called intensity. Intensity is a mathematical definition. It's usually just referred to as capital I. It's defined as power divided by area. The easiest way of thinking of it, very simply, is as the amount of energy per second that's passing through an area. Now it is a new quantity for us, so let's just check the units. We have power and loss being divided by area in terms of meters squared. So the units of intensity, very simply, are are watts per meter squared. Now, calculating it in the context of sound can be thought of one of two different ways. First of all, let's think of it in the production. As I speak to you, a certain amount of energy per second is necessary on my part to create the sound waves, which then propagate towards you along spherical wavefronts. So in that context, we can start to think of intensity now as the following. Okay, right here is a source of sound, and there is a power output, as we say, associated with the source. It's usually just referred to as P source. So it's the amount of energy per second that's necessary for me to speak to you, for example. And then the sound wave itself propagates outwards like so in a sphere. The sphere has radius r. So in this context of the production of sound, we can think of intensity, I, as being equal to P source, but then divided by the total surface area of the sphere over which that energy is essentially spreading outwards. So then therefore, the geometrical formula for the surface of a sphere, if you remember, is 4 pi r squared. So intensity, power over area, is the power associated with the source divided by the area over which all of that energy is spreading. That is the surface area of the sphere. Notice that, like gravity, intensity involves an inverse square law. Now you can also think of intensity, however, a little bit backwards, if you will, in terms of a receiver. Somebody who is listening to the sound, and we can then begin to describe it as the amount of energy per second that's passing through an area, such as, for example, the area of your eardrum. So let's say that you're now an observer or a receiver over here like so, and there's a little box here, there's a little area associated with it. The intensity of the sound wave I could be thought of now as the amount of energy that you would receive per second, call it P received, divided by the area of this little box. If you want to think of it this way, think of it very simply as the cross-sectional area of your ear. So mathematically, we kind of define intensity sort of two different ways. First, in terms of the production of the sound itself, and then secondly, in terms of the receiver. Okay, now how does this relate to loudness? Well, we use a scale to describe loudness, and that scale is called the decibel scale. Decibel scale is a base 10 logarithmic scale, and the scale is defined in terms of the softest audible sound. The intensity of the softest audible sound is called I naught, and it's really small. It's only 1/trillionth of a watt per meter squared. 1 times 10 to the minus 12, 1/trillionth of a watt per meter squared. Now that number is exceedingly tiny. So, for example, what would the softest audible sound like? Well, for example, now, Greg and Nathan sitting right in front of me, they could probably hear most of the words that I was using as I spoke with a barely audible whisper. However, on the other side of the room, Ryan, for example, could he hear me? No, and the reason for that is by the time that the sound reached the other side of the room, the intensity, in accordance with the inverse square law, had gone below a value of 1/trillionth of a watt per meter squared, so it wasn't audible to him. However, these guys sitting right in front of me could probably make out a couple of the words that I was using. Yeah.
So does it damp a lot?
So it damps out. The reason, well, it doesn't really damp out so much as it spreads out over an increasingly larger and larger surface area of the sphere. The intensity drops off according to an inverse square relationship. Okay, now before I get to the actual scale itself, let me toss a couple of other numbers here involving intensity at you. First of all, you reach a point where the sound actually becomes painful. This is referred to as the threshold of pain. The threshold of pain is an intensity of 1 watt per meter squared. If you have this much energy per second striking your ear, for example, it literally starts to damage your hearing. Because the way that your physiology essentially works is that your eardrum is basically a little sack of flesh in a membrane, and then when sound waves strike it, it vibrates. It vibrates at the same frequency as that of the sound waves themselves. That then sends nerve impulses to your brain and blah, blah, blah. When you reach this level of intensity, you're starting to damage your eardrum. And then eventually, of course, your ears can heal. Your body has the ability to do this. But if you repeatedly expose your ears to loud noises of excessive duration, then your body's ability to repair itself begins to go down. Okay, but then let's say that you get even louder still. You eventually get to a point where the amplitude of the sound wave is so large, the intensity is so big, that we don't even really think of it as sound anymore. It's just this huge pressure wave that is passing through the atmosphere. The amplitude could actually be large enough such that it starts to rupture your flesh. And this is referred to as the threshold of death. Yeah, threshold of pain is the thrash metal band, threshold of death is the death metal. Threshold of death. Threshold of death is an intensity of 1,000,000 watts per meter square. It's not really thought of as sound anymore. It's just this huge pressure wave with this huge amplitude, a really large intensity. Now, what would be an example of this? Well, you stand next to a bomb and the bomb goes off. If the shrapnel doesn't kill you, what is going to? The pressure wave itself that passes through the air is big enough essentially to basically break apart the body. That's called the threshold of death. Okay, now the actual scale itself, decibel scale, is a base 10 logarithmic scale. And the reason why we use a base 10 logarithmic scale to define it is because in terms of our physiology, what we perceive as a doubling in loudness corresponds to an increase in intensity by a factor of 10. So if you ramp up the intensity of the sound by tenfold, we perceive that as a doubling of loudness. So based upon this, we define the decibel scale in the following way. Okay, first of all, the amount of decibels, as we say, is this quantity beta right here. And then on the right-hand side of the expression, we have I naught, which is just how the scale is defined, as we'll see. And then the intensity I is the sound itself. Notice that this quantity here, by the way, on the right-hand side of the expression has no units associated with it. So the amount of decibels, that's just a name for this quantity and nothing more, and we refer to that as beta. Now the basic idea as to how this scale works is actually really easy. You'll get the basic idea with a simple problem in just a moment. I have to do something, however, that I forgot to do earlier. I'm sorry, now I have to stand at the desk. I'll just switch my projector over. I'm going to have to do that again later. Okay, let's take a look at the following problem. As I said, once you get the idea here, how the scale works is actually pretty easy. Okay, there is some somewhat confusing terminology that is sometimes used in the context of the decibel scale. This is why I've written the problem the way I did. When it says find the intensity, what we're going to be doing is solving for I. Sometimes, however, the amount of decibels is referred to as the intensity level. So I know that's kind of a little bit confusing here, at least initially, but that's the way the terminology works. Okay, once we take a look at parts A, B, and C of this problem, you'll get the idea pretty quickly as to how the scale works. And then with parts D and E, we'll kind of take a look at some cool numbers. Yeah. Okay, so this quantity here by itself, this is referred to as a bell, B-E-L. That's a really good word, by the way, for words with friends. B-E-L, that's called a bell. By multiplying it by 10, that's the decim prefix when using the metric system. So that's why the abbreviation decibel is written in that manner. This quantity by itself is just called a bell. Multiply it by 10, that gives you that decibel. Okay? Okay, now, in part A of the problem, we're first of all given that beta is equal to 0. What we then have to calculate, just from the logarithm itself, is the value of I. So just remember the basic math here of your base 10 logarithm. Here's how it works. So I set the left-hand side of the expression here equal to 0. Like so, and now just to solve for I, first of all, just divide out by the 10. And then this right here is not a natural logarithm. Remember, as I said, it's a base 10 logarithm. So then therefore, I'm going to go from logarithmic to exponential form in the following way. On the left-hand side, I'll have 10 to the 0th power. And on the right-hand side, we'll have 10 to the log of the stuff, which is just the stuff. Like so, cross multiply and solve for I. So I is 10 to the 0th times I naught, but 10 to the 0th is just 1. So the intensity of this sound at 0 decibels is I naught. In other words, it's a trillionth of a watt per meter squared. This is basically illustrating how the scale is defined. 0 decibels, by definition, is the softest audible sound that we can hear. Okay, now watch what happens as we go from A to B and then from B to C. You're going to see here very quickly a very simple pattern that emerges. So in part B, we're given that beta is 10 decibels. So 10 equals 10 log of I over I naught. And then once again, we just have to solve here for I. So cancel out a 10 from each side in this case. Just be a little bit careful in doing this. Of course, we'll have 1 left over here on the left. And then we go from logarithmic to exponential form. So 10 to the first power now is going to equal I over I naught. And then we just solve for I. So it's 10 to the first times I naught, which is 10 times more intense than this value here. So this new value is 1 times 10 to the minus 11 watts per meter squared. But this is what we then perceive as a doubling in loudness, because this intensity is 10 times bigger than this one. This then means that 10 decibels is twice as loud as 0 decibels. And that's the basic idea as to how the scale works. When you increase the intensity by a factor of 10, the amount of decibels increases by 10. That then corresponds to a doubling in loudness. Watch the same thing happen here in part C. So in part C of the problem, beta is 20. So 20 equals 10 log of the stuff. And then we just run through the math here. So cancel a 10 from each side, leaving 2 here on the left-hand side, and then go from logarithmic to exponential form. So 10 squared equals I over I naught. Cross multiply and solve for I. So this is equal to 100 multiplied by 10 to the minus 12. This is 1 times 10 to the minus 10 watts per meter squared. Well, once again, notice the simple pattern that I'm doing here in parts A, B, and C of the problem. Essentially, all that I'm doing here in A, B, and C is increasing the intensity by a factor of 10. This quantity here is 10 times as much as this. Therefore, 10 decibels is twice as loud as 0 decibels. However, this quantity here is 10 times as intense as this. So 20 decibels is twice as loud as 10 decibels. Therefore, 20 decibels is 4 times as loud as 0 decibels. And so on and so on and so on. So every 10 decibel increase corresponds to a doubling in loudness. Now when I speak to you, I'm not using my conversational voice. I'm speaking louder, of course, than I lecture here. But if you're standing right next to me, you're getting somewhere in the neighborhood of about maybe 35, 40 decibels, something like that. If you're on the other side of the room, it's a little bit lower because the intensity is lower in accordance to the inverse of square law. It drops off, remember, with distance. Okay, now let's take a look at a couple of cool numbers here, parts D and E. So in D, let's get 120 decibels. You can probably guess what this number is going to be. So 120 equals 10 log of I over I naught. Okay, do the math here once again. Cancel out a 10 from each side, making this a 12. And then go from logarithmic to exponential form, like so. And then just cross multiply to solve for I. So this is 10 to the 12th times I naught. Now remember the basics here of how you multiply exponents together. This is 10 to the 12th multiplied by 10 to the minus 12. So 12 minus 12 is 0. 10 to the 0th is 1. So this is just 1 watt per meter squared. This is the threshold of pain. Threshold of pain is 120 decibels. Now, how many of you like to go to concerts? I do. You stand next to a speaker, particularly in an indoor concert, boom, you're getting 120 decibels. Now, there's a couple of different ways to protect yourself. The easiest way to protect yourself is just move back from the speaker. When you do, you're taking advantage of the inverse square law. However, this is not easy to do in an indoor venue because not only do you have sound coming directly from the speakers, of course, but they're also reflecting off the walls and the ceiling and so on. So that's why it's always usually very loud in small concert halls because you're getting all of the reflections as well. How many of you have been to an outdoor concert? If you move back from the stage, you move back from the speakers, you probably have noticed the volume of the sound, the loudness drops off considerably. It's usually a much softer sound in an outdoor concert as opposed to an indoor concert. And the reason for that, very simply, is you're just getting sound from the speakers. You're not getting any reflections off of anything. So that's why you generally don't necessarily need ear protection in an outdoor concert if you're far away from the stage. However, in an indoor concert, you definitely do need earplugs. Now, those of you that do like to go to concerts, how many of you hate wearing earplugs? How many of you just ignore them completely, no bother? Don't do that. I'm speaking from experience. Let me briefly tell you how you want to wear earplugs. Don't buy the really gummy, waxy earplugs that you just jam into your ear and muffle everything such that you can't hear the music that you paid money to go see. Instead, what you want to do is buy some simple foam small earplugs. You can buy a pack of these things at CVS Pharmacy. They come in packs of like 50 for like $5. They're these little yellow and pink things, and you just kind of set them in your ear canal like so. You don't jam them all the way in. You just kind of put them in your ear canal like this, because that's actually going to be enough. Because what the earplugs will do is they will absorb enough of the energy such that what actually reaches your eardrum is going to be less than 120 decibels. It will be below the threshold of pain. That's an easy way of protecting yourself, and believe me, I speak from experience. These ears have been subjected to over the years, probably in the neighborhood right now, somewhere around 2,000 concerts. Now, how many of you that have been to concerts and you've started to have your ears ring afterwards, how many of you have experienced that? Congratulations, you've damaged your hearing. You are suffering from what is called tinnitus. It's also sometimes called tinnitus. I've heard the word pronounced 2 different ways. Now, when you suffer from tinnitus, your body will probably fairly quickly repair itself. You'll heal after a couple of hours and the ringing will go away. However, the more and more you do this, or the louder the sound and the longer the duration that you're exposed to, then your ability to heal itself, the body's ability begins to go down. I remember once a couple of years ago, I went to this show at a small club on Hollywood Boulevard, and I was right up against the stage, and it was loud, and I did not have earplugs with me. I had forgotten them at home. My ears were ringing for 6 days afterwards. That was not good. So, wear earplugs. All right, and then lastly, let's take a look at E. You can probably guess what E is. Yeah. Watch what happens in E. 180 decibels. So 180 equals 10 log I over I naught. Okay, do the math. Cancel out here, making this 18. Then go from logarithmic to exponential form. 10 to the 18th now equals I over I naught. And then just finish by cross multiplying. Okay, now mathematically what we have here is 10 to the 18th multiplied by 10 to the minus 12. So 18 minus 12 is positive 6. This is 1 times 10 to the 6th. It's 1,000,000 watts per meter squared. That's the threshold of death. At this point, as I said, we don't no longer even really bother to think of it as sound. It's just this huge pressure wave. So if you stand next to a bomb and it goes off, boom, that's 180 decibels basically. Now when it comes to the loudest sounds that people could be subjected to and still end up surviving it, well, probably somewhere in the neighborhood of, say, being exposed to a jet aircraft at full throttle. If you're exposed to a jet engine at full throttle, that's in the neighborhood of 135, 140 decibels, something like that. That's not at the threshold of death, but you're to the point where you're probably going to blow out your eardrums. So that particular type of sound would be, in the case of 130 decibels, twice as loud as 120. 140 decibels would be 4 times as loud as 120. This is why you always see airport workers, when they're walking around on the tarmac, they got those big earmuffs, they're damping out all of those noises such that they're well below the threshold of pain. But a jet aircraft at full throttle, 135, 140 decibels, something like that, yeah.
What about a gunshot?
Gunshot, if you're really close to the actual explosion itself, you're probably above the threshold of pain. You're probably greater than 120, somewhere around 130 decibels.
And then like the movies when they hold the gun right next to the person's head and just like shoot it off.
And then they're all fine and walking around afterwards for the remainder of the
Yeah.
scene. That's another unrealistic aspect of what happens when guns are fired in television and movies and so on. Besides not showing the recoil correctly, everybody just kind of walks around without ear damage. This is why you always see people when they're at firing ranges and stuff like that, also wearing ear protection for this reason. Yeah. You mean sonic booms and stuff like that? If you're really close to it, it can be above the threshold of pain or even the threshold of death in some cases. How sonic booms are created we'll actually cover at the end of this chapter after we get back to the magic number. Okay? Okay, now I've been describing here throughout my discussion of intensity levels, the inverse of square law. Let me do a specific example that illustrates exactly what I mean by that. Let's take a look at the problem. So I mentioned earlier that an easy way to protect yourself when you're exposed to loud music, for example, is just move back from the speakers a little bit. This will illustrate exactly why that is. Incidentally, while you're writing down the problem, one thing I did forget to mention earlier is that the Richter scale, which describes intensity associated with seismic waves, is essentially almost identical to the decibel scale. It's basically a base 10 logarithmic scale. It, of course, has a different definition associated with it, as opposed to I naught when talking about the decibel scale, but it's more or less the same thing. One thing that the Richter scale does not do, however, is it doesn't put the 10 in front of the logarithm. So you end up with just small numbers. But the basic way that the scale works is exactly identical to that of the decibel scale. That is, if you have a Richter scale 6 earthquake, that's 10 times more intense than a Richter 5. It's 100 times more intense than a Richter 4, and so on. But other than that, it's basically the same scale. Okay, what I'm going to do is use this example here as a means of coming up with a nice illustration of how the inverse square law works, where you could actually describe the intensity of a sound with respect to another value at a different distance. Okay, here's what I mean by that. So we have a person standing 3 meters away from a speaker. The person hears 120 decibels. Remember that that's an intensity. I'm going to call it I1, 1 watt per meter squared. That's the threshold of pain. Okay, the person is standing a distance R1 equal to 3 meters away from the speaker. So the situation that's being described here in terms of the speaker basically just looks like this. We have the power output from our source, and then that energy spreads out like so over the surface area of a sphere, where the radius of that sphere is R1. So in terms of the production of this sound, this intensity I1 is equal to P source divided by 4 pi R1 squared. But now we make a move. We move 3 times further away from the speaker. So now we're given a second value of R. Call it R2, and it's 3 times R1. So you move further back from the speaker, sound wave propagates outwards like so. You end up, of course, with a larger sphere, in this case of radius R2. Now the intensity of the sound at this greater distance away from the source, call it I2, is still equal to, in the numerator, the same P source as it was before. It's still the same speaker, of course. But now we're dividing out here by the surface area of a larger sphere. What I want to do here in this problem is relate I2 and I1 together. And the way that I can do that is to notice what's common to both of these expressions. Both of the expressions have the same numerator. It's the same P source of each. So what I can do is, say, solve for P source here by cross-multiplying this up to the left-hand side. Solve for P source here by cross-multiplying this up to the left-hand side, and then setting the quantities equal to each other. This will allow me to relate the 2 different intensities, I1 and I2, together. So here's then what that looks like. First of all, from the upper left, P source will be equal to this when you cross-multiply. And then over here on the right-hand side, if I solve for P source there, that would be equal to this, once again, when you cross-multiply. Okay, notice that the 4 pi cancels out. When the 4 pi cancels out from both sides of the expression, you end up with the following quantity. And now when I apply this quantity here in blue to our problem, now you'll see the basics of how the inverse square law here works. Think of it merely like this. So we're given in our problem that R2 here from the top board, excuse me, R1, was equal to 3 meters, and then yes, R2 from the top board is 3 times R1. So I'm going to replace the R2 here with 3 times R1 to give me the following. Like so. And then if we do the math here, notice that the R1 squareds cancel out from both sides. Cancels here, and it also cancels here. And then what's left behind here is a 3 squared, which is 9. What I'll do is I'll take that 9 and move it down into the denominator here on the left-hand side. That will then give me an expression for the intensity I2 in terms of the original intensity I1. So cancel out all the R1s, move the 9 down here to the denominator on the left-hand side, and you basically just end up with this. So in other words, if you move 3 times further away from the source, as we've done here in this problem, then the intensity is 1 over 3 squared, inverse square law. It's 1 over 9 of the original value. If we just move twice as far away, it would be 1/4. If we move 4 times further away, it would be 1/16, and so on and so on. So in this particular case, if you move 3 times further away from the source and the intensity is 1/9 of the original value, notice that this is pretty close to about 1/10. So the sound is then therefore about 1/10 of its original value. This then means that it's half as loud. So instead of being 120 decibels like it was originally, it would be about 110 decibels. 110 decibels is half as loud as 120 decibels. You're below the threshold of pain. That's obviously the easiest way to protect yourself. Just move away from the speaker a little bit. You're taking advantage of the inverse square law. That's how it works. And then lastly, for problems such as this, it's very easy to kind of get the idea in your head that there's a lot of energy associated with sound waves. Like, for example, just normal sound as I speak to you here in this classroom. That's actually not the case. Total amount of energy associated with sound waves, as you'll see, is actually next to nothing. Let's take a look at our last example to illustrate that in the following. The numbers that are given in this problem here are accurate, by the way. I'll explain as we go. So let's say you're standing on the other side of the room from me. You're at a radius of 5 meters away. And you're hearing as I speak, let's say an intensity of 1/1000th of a watt per meter squared. That's actually pretty loud though, that's 60 decibels. Now if you're standing close to me right now, and you hear me speak, as I said earlier, you're hearing maybe 35, 40 decibels, something like that. So 60 decibels would have to be like screaming at you like this or something like that on the other side of the room. So what we want to calculate is, first of all, how much energy per second is necessary for me to do this in part A of the problem. And then in part B of the problem, we'll do the following. Let's say that your ear has an area, and this is an accurate number, by the way. This is about how big your eardrum is. It has an area of 5 times 10 to the minus 5 meters squared. How long would you have to be continuously exposed to me yelling at you in order to receive just 1 joule of energy? So how long do you think you would have to be sitting there with me screaming at you continuously such that you receive through your ear the total amount of energy that is necessary for me to do this? 1 joule is about the energy necessary for me to take my phone and raise it a couple of feet above the ground. So take a wild guess. How long do you think you'd have to be sitting here listening to me continuously scream at you such that you get 1 joule of energy like so, the energy necessary for me to lift the phone? Just a ballpark guess. A week maybe. A week, okay. A couple of years, okay. Something like that, we'll see. Huh?
1 hour.
1 hour, okay, so we've got this wide range of guesses here. As much as an hour, 3 hours, to a week, to a couple of years. Let's see.
Let's add a day.
Yeah, let's put money on it.
I'm not spending money on this.
No, I don't want to bet on it, because I would win all of your bets. Actually, it's not a bad idea after all. Because I know the answers to all these problems ahead of time. All right, let's think of it like this. So we're given 60 decibels, the intensity is 1 times 10 to the minus 6 watts per meter squared. Now in part A of the problem, we're just talking about the production of the sound. So we've got a source here, P source. The energy spreads out like so over the surface area of our sphere. The radius of the sphere here, R in our problem, remember, is 5 meters. So you're on the other side of the room from me as I'm screaming at you. You're getting the intensity at this particular value. Okay, now in part A of the problem, we're asked to calculate the power output of the source. As we'll see, it's next to nothing. So the intensity, I, is P source divided by the surface area of the entire sphere over which that energy is spreading, 4 pi r squared. Just solve for P source. So P source is equal to I times 4 pi r squared. So just multiplying it out here, easy enough to do. We're going to end up with, however, a very small number. So I have the intensity, which is 1/millionth of a watt per meter squared, and multiplied by 4 pi r squared. So pi times 5 squared, which is 25. And you end up with, it's actually a multiple of pi, 3.14 times 10 to the minus 4 watts. So that's how much energy is necessary per second for me to produce the actual sound wave as I'm screaming at you. Now let me kind of give you a nice little comparison regarding this number. How many of you are kind of like into stereos? Anybody here like into stereos, etc.? Like you like high-end stereo equipment, etc.? You go into Best Buy and some blue-shirted chipmunk comes up to you and he tries to sell you a speaker and he says, look at these speakers. These speakers have an output of 200 watts. And you go, wow, those are kick-ass speakers. I'm going to go out there and get those speakers that are 200 watts. Well, notice how small the wattage is associated with the actual sound wave itself. So if you get bamboozled by some kid in a blue shirt selling you 200 watt speakers, just be aware of exactly what it is that you're buying. Well, most of that energy, frankly, is just going into the electronics themselves. The actual sound wave, the wattage associated with it, is next to nothing. And we're talking about something fairly loud, 60 decibels. So then therefore, you're never going to go into Best Buy and see advertisements where they're screaming at you, our speakers pump out 3.14 times 10 to the minus 4 watts. And everybody's going to look at that and go, I don't want those speakers, I want the 200 watt speakers. Just be aware of what it is that you're actually buying. Okay, now, let's take a look at part B. Now, part B is kind of like having a receiver, like I described earlier today, the fourth portion of my lecture. Right over here, we'll say is U. And you've got an area associated with your eardrum, that's the number that's given here, 5 times 10 to the minus 5 meters squared. We want to calculate how long is necessary for you to receive a total of 1 joule of energy, the energy necessary for me to basically do something like this. In order to calculate that, we'll use intensity once again, but now in this context. That is, the intensity now will be the energy that you receive per second divided by the area of your ear. Okay, now we'll calculate P receive, the amount of energy that you receive per second, and then from there calculate the time that is being asked for. So the remainder of the problem here is just 2 short steps. I'm going to calculate P receive. It's just I times A after you do the math, and this is going to be exceedingly small. So the intensity, 1 times 10 to the minus 6, multiplied by the area of your ear, 5 times 10 to the minus 5. There you go. And that's 5 times 10 to the minus 11 watts. So this is how much energy per second you're getting through your ear. And then lastly, we'll calculate the time by just remembering the following. Remember that power, you receive, is equal to energy, E receive, divided by time t, where the energy that you want to receive here in this problem is just 1 joule. So I'm going to calculate the time here by just cross-multiplying. I'll get a time in seconds. It's the energy that you receive here in this problem total, 1 joule, divided by the rate at which we receive it. 5 times 10 to the minus 11 watts. So I just had to take the inverse of 5 times 10 to the minus 11, and you end up with 20 billion seconds. That's 2 times 10 to the 10th seconds. This is considerably more than an hour. It's considerably more than a week. It's considerably more than a couple of years. It's several human lifetimes. If I divide out by the number of seconds in a year, just doing the conversion here really fast, it's about 635 years. So you would have to sit there for 635 years with me screaming at you continuously to have just 1 joule of energy go through your ear. That's the amount of energy necessary to lift the calculator. So if you're talking about relatively soft sounds, the amount of energy associated with sound waves is next to nothing. Yes, when the sound becomes very loud, then the energy, of course, can go up dramatically. How many of you at concerts have ever felt your clothing ruffle from really loud noises coming from the speaker? Well, those really loud sounds near 1 watt per meter squared, yeah, then you're starting to get a significant amount of energy. It's enough to actually feel it a little bit. But when I speak to you, the energy that's present there is next. All right.
So Charlotte, there is a thing where these students in the University of Minnesota reason sounds like extinguished fires.
Oh, yeah, I saw that.
Yeah, by focusing the sound waves in a specific direction. When you do that, you're basically using constructive interference to amplify the sound. Okay, now speaking of amplifying sound, let's get to musical instruments.
That's a big one.
Yeah, nice sight. I'm always looking for means of doing this. Teacher shortage. How many of you play an instrument? A couple of you do? Okay, good. And again, with the simplest type of musical instrument, and the simplest type of musical instrument is just a single tuning fork, like so. Now when I strike this tuning fork, it's going to vibrate back and forth at its natural frequency. In this case, it's a frequency of 384 hertz. So as the individual tongs here, just think of them as sticks, vibrate back and forth like so 384 times per second, that then brushes up against the air molecule, causing the propagation of sound waves outwards from that point at exactly, of course, the same frequency. And that is then what reaches your ear. However, if I strike the tuning fork initially very hard, you're going to hear a really annoying high-pitched sound. Like so, that you're hearing very high-pitched. Where does that come from? Well, if you hit the tuning fork really hard on each individual tong, you get this really complicated waveform that kind of looks something like this. And it has a really large frequency, resulting in that really annoying high-pitched sound. However, that usually damps out fairly quickly. And then what remains is just each individual tong vibrating back and forth like so, kind of like sticks at the natural frequency of 384 hertz. You'll be able to hear this if I strike the fork rather softly just against the sole of my shoe. That sound that you hear, let me give it a little bigger whack. That sound right there, that's the 384 hertz. How I'm using the table, by the way, as an amplifier. Like so, we'll get to that a little bit later on. But that hum that you were hearing was the 384 hertz then to the fork itself. Okay, now when it comes to musical instruments, perhaps one of the most versatile and also easiest to explain as to how they work are string instruments. So I have an example of a stringed instrument. This is my really cruddy looking guitar right here. What I have here are 4 guitar strings that are placed under tension here from the opposite sides of each peg, like so. And then let's say that I begin by plucking one of the guitar strings really hard, like so. And you hear kind of that annoying high-pitched twangy sound. Just like giving the tuning fork a really good whack, if you pluck the string really hard like so, on the string itself, you end up with this really complicated high-frequency wave form, giving you that high-pitched twang. However, if I pluck it rather softly, say like so, a nice clear tone that you hear right there, that's just nothing more than the n=1 standing wave for string that is being fixed at two ends. Just like we saw in chapter 15, say with our mini lab on standing waves just prior to spring break. So when a string is plucked, the n=1 standing wave appears. So you just end up with the following n=1 standing waveform that looks like this. Now, as I said, if you pluck the string really hard, the individual string itself has this complicated waveform along it like so, giving you that high frequency twangy sound, and it usually damps out, however, very quickly, and then therefore the tone that persists is just nothing more than the n=1 standing wave. Now, in the case of this guitar, however, not only is sound being produced by the vibrating string, but when I do pluck the string and set it into vibration, it actually causes the entire board. It causes the entire guitar to vibrate at the exact same frequency. So you're not just hearing sound coming from the string, like so, you're actually also hearing sound coming from the board. Because, for example, Greg, if you go ahead and hold the board for a moment, and now I'll pluck the string, feel the board vibrating? Absolutely. So you're listening to sound here. It's not just coming from the string, but it's also coming from the board itself. Now, this is obviously a really cruddy guitar. However, if you do have a very well-made instrument, when you play a note on the instrument, what actually appears on the body of the instrument itself is a pattern of nodes and antinodes. And the antinodes vibrate with the largest amplitude, giving you nice, loud, clear tone. In other words, the mere act of me plucking the string will actually cause the board itself to resonate. A well-made instrument will do this equally, essentially, with every note that is played. Under the right conditions, you can actually see the patterns of nodes and antinodes that appear on the instrument itself. Let me show you. Dahlia, I'm sorry, I need to stand up on your desk. Switch over again. All right, now, what I have right here is, first of all, a function generator that is then connected to a speaker, which is this circular thing down here. Think of that as the guitar string. And then attached to the speaker right here is this metal plate. Think of that as the body of the guitar. And then what I'm going to do is set the body of the guitar here into vibration, like plucking the string, for example, by just turning on my function generator. Like so. Notice that the sand that I've placed here on the metal plate is shifting around a little bit because the plate itself, for example, is vibrating. It's vibrating because it's attached to the speaker. So think of the speaker with the function generator as the guitar string. Think of the metal plate as the body of the guitar. At certain frequencies, however, I can get the metal plate to resonate. I can end up with a pattern of nodes and antinodes. Specifically on this plate, I think I can get like 4 or 5 of them. Like so. Now if I move off of that frequency, notice that the sound is rather soft, like so, because the plate is no longer resonating. But if I go down to that resonant frequency, then you end up with this pattern, like so. Now where is the sand, by the way? Is it at the location of the antinodes or the nodes? Remember, antinodes is big vibration, nodes is no vibration. So where does the sand go? It goes to the nodes, that's right. In other words, the antinodes push all the sand into the nodes. So you then see what the pattern looks like on the metal plate as specifically the position of the nodes, that is where the sand is. Now there are several resonant frequencies of this metal plate that I can reach with my function generator. That was one of them. There's another. Notice how loud that was, because not only are you hearing sound coming from the guitar string, the speaker, you're also hearing it coming from the body of the guitar, the metal plate. Like so. And I'm going to hit a few more. There's another right there. Right about there. And then, there's a couple more I think you can hit. There's one right there. So. There's another one right there. You make this one into a t-shirt. Might be one more. Yeah, right about there. That one's really neat. Right about there. Looks like a bow tie. It's really cute. I'm close to another one in here. At these really high frequencies, just minute adjustments here in the dial changes it by quite a bit. So I'm not quite able to hit it by just doing this by hand. Yeah, but there's another one in there somewhere. Looks like there's another one in here too. Yeah, somewhere around here. There's another one. But it's obviously a lot easier for me to hit it at the lower frequencies. So there's the first one, basically that circle. There's the second one. And just one more again. There's that one. So. Okay, these patterns, by the way, have kind of a strange name. They're named after somebody. These patterns that appear, they're called Chladni patterns. Named after somebody. The Chladni patterns here, as they're called, is this pattern of nodes and antinodes that appears on the body of the instrument when it's played. Here's the body of the instrument when it's played. So a well-made instrument will basically have these patterns appear here with every note. Now, during period 2, when I showed this demonstration to the students, Ari Kirsch called up something on YouTube, which he then subsequently sent to me, that shows some really awesome demonstrations of Chladni patterns set to electronic music. I'll go ahead and post it on Schoology after the period today. I encourage you to take a look at it. It's actually a really cool video using some pretty sophisticated equipment. Yeah.
Is that the same thing with like fire, using that video?
I will actually show you that demo with the flame tube. I'll do so, however, late next week. But if you've seen that version of a demonstration that's similar to this involving a flame tube, I've got one. I'll show it to you next week. Okay? Yeah.
When it sounded like he was kind of vibrating a lot faster, vibrating, that's resonance?
Yeah, so you get the loudest tones. I mean, the whole time the plate is vibrating. It's just that only at specific frequencies, the natural frequencies of the plate itself, will you get the vibration at its largest. That's when it pushes the sand into the batteries.
And it's like
And that's when it got really loud. And the reason why it's a nice, simple geometrical pattern is because we're just talking about a rectangle. So it's easy to see the patterns. If you've got something with a complicated shape, such as, say, the body of a violin or a guitar or something like that, you don't end up with all these nice straight lines and so forth. You end up with kind of like all these little wavy type of forms that show the notes and the anti-notes instead. It's much more complicated. Okay? It's actually not as aesthetically pleasing as something similar as this rectangular plate. Okay, now just getting back to string instruments themselves, just regardless of the Chladni patterns. The reason why string instruments are so versatile is because of the frequency equation associated with this type of a waveform. So if we jump back in chapter 15 for just a moment, remember that the fundamental frequency, also called the first harmonic frequency, is the quantity V over 2L. Now the V here can be initially a little bit confusing. The V is not the speed of sound. The V is the speed of the wave on the string itself. Also from chapter 15, remember that the speed of the wave on the string is equal to the square root of the tension divided by the linear mass density. If I replace the V here in my frequency equation with this little speed expression here, then essentially this equation here shows us why string instruments are so versatile. That is why they can play such a wide range of notes. Because you can essentially control a bunch of different things. So for example, if you're going to just pluck a single guitar string, what is probably the easiest way to change the note that is played? All that you have to do is change the length. So for example, if I just pluck the string as it is, like so, and then place my finger down, pressing the string to the fretboard like this, I make the L smaller. So if I make the L smaller in the equation, then the frequency is bigger. It's a higher pitched sound, like so. So that's the obvious, easy way of changing a note that's played on a string, just change its length. You could also change the string itself. That's manipulating the value of mu. So the value of mu here, remember, is the density of the string. Some of the strings are thicker than others, so I have 4 different examples here. So it's a really crappy guitar, as I said, but you can just change the string, and then you can also change, of course, the tension. So if I don't tighten the tension first, for example, here's what the string sounds like. So, and now I'll tighten it up. If I increase the tension, then the frequency goes up. It's a higher pitched sound. Like so. When it comes to playing an actual guitar, however, some skilled players can in fact play a couple of maybe the higher harmonics. Instead of the n equals 1 standing wave, skilled players can play the n equals 2 standing wave, which looks like this. And then the frequency here is 2 times the value as it was up on the top board. Now with this simple acoustic guitar, the easiest way for me to do this is to actually place the board flat like so, and then just kind of pinch the string from the side. I'm not going to press it down on the fretboard. I'm just going to pinch it to the side like so. And then when I pluck the string in this case, sounds like crap. But when I pluck the string in this case, it's both sides that are then vibrating like so. My finger is basically right there. So without doing it, sounds like that. And then by doing it, sounds like that. So skilled players can play some of the higher harmonics. It's actually easier to play the higher harmonics on electric guitars. And the reason for that is because you take advantage of feedback. Do you know what feedback is? This is where the sound that is coming out of the speaker itself, you use that sound to keep the string vibrating. So it just feeds back upon itself. So the force that keeps the string vibrating is not necessarily you by plucking it, but just the sound coming from the speaker. That'll keep the string in vibration, and then you can just place your fingers along the string like so to play some of the higher harmonics. This is a lot easier to do with an electric guitar as opposed to a simple acoustic guitar. Okay. All right, that's as far as I'm going to go today. That gets us even with everybody. Let's take a look here at the board. I have shortened the WebAssign. I basically put the second half of it off until next week because I really didn't have time today to do example problems associated with string instruments, even though the examples are pretty easy. But we'll just hold that off until next week. So then therefore, the only thing I have to do tomorrow are the following 3 problems here from chapter 16. They're all intensity and decibel problems. They're all really okay.
All right, we did it. 3 problems tonight.
Before I take it apart, does anybody want to see it again up close? Yeah, before I take it apart. We're getting close. It's 1 or 2 weeks to go.
I don't wanna go this way.
Well,
I'm going to go down to the low end first.
right.
It's really cool if you look at it from the side, you can see the sand bouncing off the back of the
You're
video.
on a domain, right?
So that's about the first
I mean,
one.
I'd rather say anything. I was hoping for like a line of the boss shape.
Huh? No.
I never did before.
It's probably because it's not fun.
I started hiking in the thing.
I follow.
But they're like, you're
And
friends.
he told me.
Do you ever find someone to cover you?
Huh?
Do you ever find someone? Wait, why did you do that from the beginning?
I just went to this.
Oh, wow, it is.
Can I stop it?